Hi friends. This video is going to be a little bit about lines. And one of the things that I hope that you already know about lines is that lines are an infinite number of points that sort of connect together. They run together, if you will. And so usually we talk about these integer points, right? The points like 4, 4 here, or 3, 3, or 2, 2. But all of the, for any x value I can imagine, for any value that I can think of along this x-axis, 2.5 or 2.74, for any value I can think of, there's a corresponding y value, and only one corresponding y value. And these lines are infinite not only in between points, but also if I were to zoom out on the line, these lines keep going, right, forever and ever. In a specific direction, or what we would call a constant rate of change. And constant rate of change, or the slope, is how we talk about how the line rises, or sometimes a line decreases or goes down over time. So we might say that that line travels down one step for every one pace over that you take, right? The change is down one for every one step over. Or maybe it's a positive one slope. Maybe it goes up one for every one step that you go over, right? Maybe it's a steeper line. It goes up 2 for every one that you go over. So we're really thinking about how high does that line grow for every step, for every X pace that we go through. Does it grow a lot? Maybe it grows 10 paces. We go over one, it grows 10. Maybe it grows just a little. Maybe it's a nice shallow line, right? It only grows 0.3. So if we go over, we notice it's only about a 0.3 higher, right? At 2, it's at 1.3. So every line can be described by the rate of change that it has, by its slope, its constant rate of change. But it also can be described or can be altered based on the point that you select, right? Maybe I want that point there, but maybe I'm going to take another point. Maybe I'm going to start over here at negative 5, 5. Maybe that's the point that I'm starting with, and then I'm going to change, or I'm going to grow 0.3 for every step I go over. Or maybe I want to start over here, right, at negative 10, and maybe I want this point to be, I don't know, this one up here. So here I've got a point and I've got a rate of change that's constant. So for lines, we really want to think about what point are we talking about? Where on the coordinate plane are we thinking about? And then how is it growing or shrinking from that point? How is its change happening? Knowing, of course, that that change is going to be consistent over all time in both directions. So let's talk about a couple of attributes of lines that make it easier to talk about. The first one that we really need to get a handle on is slope. So the slope of a line is just a ratio. It's a comparison of two values, and it's a comparison of how much the line moves up, how much its vertical changes, compared to or divided by how much its horizontal changes. So for this line here, we've got these points here, and we can see that in between two of these points, for example, here we've got 0.22 and 0.74. This change goes up 2 values for every 5 values that we go over. In other words, we're going, our movement or our change is 2 for every 5 we have. And we could express that as a decimal if we wanted to, as 0.4. Though I tend to like to leave them as fractions. Now the interesting thing is if I chose two other points on this line, like let's say I chose these first 2 points. And this point here is 1, 2, 3, 4. I'm just going to mark some of these points in here. That's -5, 2, 3. So that's -8. -2 is that point, and this point is -3, comma 0. So if I were to consider these rates of change here, this line goes up 2 and over 1, 2, 3, 4, 5, over 5 spaces. So again, the rate of change for this section is still 2 for every 5 steps over we take. For this section 2, it would be 2 for 5. You might even notice that if I were to take this first point and go to the second point here, I would go up 4 spaces for every 10 that I went over, which would give me a slope of 4 over 10, which you might already notice is 4/10, that I can simplify that to 2 for every 5, or 0.4 again. So no matter how I look at this ratio is going to stay consistent across all of these points. And that's the slope. Again, often in language we'll say rise over run for slope, and we can express that as the change in y. This symbol here, delta, meaning change. So the change in y, how is y changing for every point, and how is x changing for every point? Not only can we see it from the image, but we can see it from the points that we might use as well. I'm just going to erase this a little bit to clear up some visual space. So for example, if I might look at some of these values, maybe as a table. Maybe I'm going to think of these as the x values and the y values of these points. So I could list out some of these points. I have -8, -2, and my next point is -3, 0, and my next point is 2, 2. And notice that my y value is changing every time by the same amount. It goes up 2, it goes up 2. I didn't put that next point in, but I could, 7, 4. It goes up 2. So my change in y is equal to 2. And I could look here and I could see that my x values are changing as well. From -8 to -3, that went up 5. From -3 to +2, it went up 5. From 2 to 7, it goes up 5. So that rate of change is 2 over 5. Again, the same slope that we saw from the picture, that it went up 2 for every 5 that it went over. For those of you who like to think of a formula, who like a rule that you can apply, we've got one. And the rule that we use is that we find the difference. We find the distance in our y values. How far is it from this y value here? Remember that the y values are the second, right? What's the distance? How do I get from this y value to this y value? Remember that distance is the same as difference. So I could just subtract. So I want to go from 2 to 4. In other words, I want to know how far is it between those 2 points. 4, take away the 2 that I started from. For the x values, I'm going from this x value of 2 all the way over to the x value of 7. So I want to know the distance between 2 and 7. So if I'm at 7 and I started at 2, what's the difference? What's the distance? And that gives me a distance of 2 over 5. So again, thinking of that, this was my x1 value, and this is my y1 value, my first y. This is my x2 value, and this is my y2 value. And I can just insert those straight into the formula, straight into the rule. So those are three ways that you can identify the slope of a line. Because it's so useful to have a slope, so the slope of the line tells us how steep the line's going to be, but we also want to know which line we're talking about. Am I talking about this line here? Or maybe you'll notice that I could have a line with the same steepness, but maybe it's up here. Or maybe that line with the same steepness is all the way down here. Right? Maybe it's coming through a point over here. So notice all of these lines, they have the same slope. They're parallel lines. So they're related, but I would like to fix it. I'd like to know that it's that line in particular that I'm interested in. So I need to also fix it around a point. And that brings us to the point slope form of a line, which is a really useful way for fixing the equation of a line. It comes straight from the slope formula, this formula of finding the difference between the y's and dividing it in the difference between the x's. In fact, with a little mathematics here, I could just solve this equation for y. So by multiplying by these x's on both sides. And then these will cancel out, and I'm left with y, in this case y2, because I was dealing with a specific point, minus y1, which is equal to m times the quantity x2 minus x1. But I want to generalize because I don't know where that second point is. In fact, I want to leave the opportunity to talk about any point on that line. So I'm going to generalize these cases by just eliminating that second point's specific nature, right? I'm not talking about a specific x2. I'm talking about any x and any y. And so then notice if I just were to flip this equation, I would have the same rule, y minus y1, which is equal to m being slope times the quantity x minus x1. So there's this point here, the point x1, y1, that came from the slope formula. That was the number that you would have put in here for x1 and y1. And then we've generalized the x and the y so they could be any points. So using this rule, y minus y1 equals m times x minus x1, we know that this m is still representing the slope. And x1, y1 represents a point somewhere on the line, fixing the line in a specific space. So I can look at a series of examples for this line. If I were to look at this line here, this line goes through points, for example, 2, 2. And we know from above that the slope of this line was 2/5. So I could write the equation here as y minus, take the y1 value. Remember that it's x1, then y1. So y minus y1, which is y minus 2, equals, the slope is 2/5 times the quantity x minus the x1, which in this case is 2, so x minus 2. And that's one way to write the equation of the line, where the point is 2, 2, and the slope is 2, 5. Now, one of the neat things about point-slope form is that I could choose to write a different form equation of this line. Maybe I would want to write, this point we said was 7, 4. Right? So maybe I want to write the equation from this point. I want to talk about this point. So I could write y minus 4 equals 2/5 times x minus 7. Or maybe I'm interested in talking about this point here, which we said was negative 3 comma 0. So I could write y minus 0 equals 2/5 times x minus negative 3. Notice that since here we're minusing a negative, we're going to change that value to a positive. So it's important to note that when you're looking at the equation in point-slope form, what sometimes at first glance might appear to be a negative 2 is actually a positive y ordinate, right? A positive value went in there because the rule is that we're subtracting. If you see a plus sign, it means that a negative value went in there. And we can use this point-slope form then to graph points, graph lines on our coordinate plane. So for example, I could take a look at this equation and I could see, well, I've got an x1 value here of 2. I've got a y1 value of 4. And I've got a slope of negative 1/3. So let's just write down that information. My slope is negative 1/3. My x1 value and my y1 value, so x1 is this with the x, right? In the parentheses with the x is the x1. So that's 2. And y1 is with the y, so that's 4. So now I could graph it. I can find this point in the universe of my coordinate plane. Over 2 up 4. There's my point 2, 4. And then use the slope, right, to find the rise over the run. So this slope goes, this line comes through this point and goes down 1 for every 3 that it goes over. So down 1 over 3. Looks like there'll be another point right here, right? Down 1 over 3, there'll be another point right here. You can also think of lines as going up the other way, right? Up 1, backwards 3. Up 1, backwards 3, or positive 1 in the rise, negative 3 in the run. So this line, if we can extend it through these points, will continue in that constant rate of change in both directions infinitely through this specific point, 2, 4, given in this equation. Let's try one more example, and then I'm going to let you try some of your own practice on this before we go on to some new topics. So let's take a look at this one. Let's identify the point that we're interested in. So here we're interested in a point, an x1 value of 1, but take careful notice of the sign here. This positive sign, the rule should be x minus something. So in order to have a positive sign, we must have had minus a negative value. So this 1 here must represent a negative 1. So our value is negative 1, comma, and the y is minus, like it ought to be, 3, so 1, comma 3. The slope is right here, right in front of those parentheses, so the slope is 2. So let's graph the second line. So here I find the point negative 1, 3, 1, 2, 3. There we go. And I'm going to rise 2 for every one I go over. Sometimes it's helpful to write these as a fraction still, right? A whole number as a fraction is 2 over 1. So I'm going to go up 2 over 1, up 2 over 1. Okay. And let's take a look at where that line's going to go. Let's maybe make this line a different color, make it a green line. Okay, so this line is going to go through this point, -1, -3. I'm sorry, -1, +3. Goes through the point, -1, +3, and then keeps growing, going up 2 for every one it goes over. Nice steep line. And it's going to go infinitely on in this direction as well, forever. So that should actually be an arrow that other way. I'm just going to draw it on. Okay. So why don't you take a look at some examples with graphing points and slopes, and graphing in point slope form before you move on to the next topic.